The problem of Lab 4 was to use the principles of energy conservation and current conservation to make predictions about the behavior of circuits and compare those predictions to the values recorded in the simulation. And for the results, I found that during the experiment, all the results that I found followed the predictions I made prior to the experiment using the information we know about circuits. This lab was done by using the FET circuit construction kit, and circuits of different types were constructed and analyzed using virtual ammeters and voltmeters. And we experimented with several combinations and kinds of circuits, including circuits that had capacitors, resistors, light bulbs, and resistors in parallel, in series, and more. So prior to the experiment, I predicted that all of my results would follow the relationships between current, resistance, and potential difference that we studied in class and defined by Ohm's law and Kirchhoff's loop and node rules, which we will go into more detail later, and I observed that that was the case. And so in the rest of this report, I will go over the physics principles involved and discuss my results in more detail. For the physics principles involved, we first have Kirchhoff's loop rule, which we can see demonstrated in the figure down here. And so this says that potential energy change is 0 for a loop. And Kirchhoff's node rule says that in steady state, the electron current entering a node in a circuit is equal to the electron current leaving that node. So here the current going into this node will be the same as the current coming out. For resistors, a resistor is a passive electrical circuit component that uses electrical resistance to do things like reduce current flow, an example being a light bulb. A capacitor is a device that stores electric potential energy in an electric field. In circuit analysis, we can combine the Newton road rules and Ohm's law, and that allows us to create a system of linear equations that we can use to solve for the current, resistance, and voltage across different parts of the circuit. And so across overall circuits, the potential difference around an entire circuit is 0, as defined by the loop rule. And across individual components, we can find the potential difference using Ohm's law, which is that the potential difference is equal to the current times the resistance. And so all the circuits we used were in steady state, which means that the current flow is constant. So here is our results. So based on Ohm's law in this circuit setup, we have 2 ammeters, 2 batteries with a total potential difference of 3 volts, and then 2 resistors in series. So based on the node rule, I1 will be equal to I2, and we predicted that to be 0.02 amps, which is true. Here we replace an ammeter. We place the voltmeter. We place the ammeter with the voltmeter, and so the voltmeter reads -3 volts, and the current throughout the rest of the circuit is 0 because the resistance in the voltmeter is very high, almost infinite, so no current flows out of it. Here, when we put an ammeter in parallel to the circuit, the current in the circuit increases because the ammeter provides a path of least resistance for the current to flow through, meaning that it will not flow through this 100 ohm resistor, and that the current will actually increase. And so here we have the setup of our circuit, and in this setup we measure the potential difference across each component of the circuit using the voltmeter. And here we have the results from those measurements. You can see that in many parts it's 0 across the wires and ammeters, but it's positive 3 volts across the batteries, and then between the 2 resistors it adds up to -3 volts, and so positive 3 volts minus 3 volts is 0, and the round trip potential is 0, which is what we expected. And so here we graphed the potential versus the position in the circuit of this circuit, and so the electric field is the negative gradient of this potential, so the slope of this graph is steep where the electric field is large, and as you can see it starts at 0 and ends at 0. Here we discharged light bulbs. So we connected a 10 ohm bulb with a 9 volt battery and a 0.2 farad capacitor, and we measured the time for the capacitor to charge and discharge, and we did the same thing again using a 20 ohm bulb. So as you can see, it takes a 20 ohm bulb about twice as long to charge and discharge compared to the 10 ohm bulb, which is what we should expect. And the current spikes initially, but then drops back down again while charging, and then slowly goes to 0, and it's the same pattern with discharging, but slightly different in reverse. And so here we looked at time-dependent voltage across the discharging capacitor. So here we set up a 9 volt battery and a 30 ohm bulb and a 0.2 farad capacitor. And so first we charged the capacitor, and then we discharged it and measured the voltage versus time for 20 seconds. And so this allowed us to determine our RC value, which is called the time constant of the circuit, and it's the time at which the voltage difference is dropped to 1/e its original value. And so when we graph the natural log of the voltage differences, we graphed divided by the initial voltage difference versus time, we get this line, and so the slope of this line is equal to -1 over RC value, and as you can see, the predicted RC value was 6, and our experimental was 6, which is good. In conclusion, our conceptual questions. So if we did this lab in real life and used an actual ammeter instead of an ideal simulated ammeter, the difference is that a real ammeter has resistance, so it would have added resistance to the circuit, whereas in this simulation, we assumed an ideal ammeter that had zero resistance. And so if we did this lab in real life and used a real battery to charge a real capacitor, our capacitor should theoretically reach full charge instantaneously, and this would not actually happen though because there is some resistance in the wires connecting the battery and the capacitor. And so throughout this lab, we better learned how to analyze and evaluate circuits, and although this lab was done virtually and using real components, its results are not entirely indicative of what real-world results would be. Thank you.